Hi, this is the report for ASRM 595 course, and our topic is drug overdose deaths. Below is our members and the link to the codes. Then this is the motivation for why we want to predict overdose deaths, and we are trying to see if we can use a simpler model but still maintain the predicting performance. And this is the introduction of the data that we use the data from US and the time range, the sample size, and we decided to use predicted OD count as our label. And the reason that we don't use reported OD count is because they are often incomplete and some overdose deaths require lengthy investigation, including toxicology testing. And our features are months, indicator, state, and percent pending investigation.
Here's our sample data. We can see that we have 12 columns and we have 60,000 rows. For data preprocess, we rename some of the column and convert data type. Then we define our debug dataset and working dataset. And then we do the data exploration. Firstly, we remove all the unnecessary features like footnote symbol. And then when we check the variables, there are some overlapping classes under variable state and indicators, like US, which is under state and is the sum of other states. So we remove them. And then we construct different table to explore our data. In the table of drug overdose deaths, we can observe the trend is going up year by year. Then in the table of deaths per state, we firstly use the unnormalized data, which indicates that California has the largest number of deaths, but we know that the number per death was influenced by the population. So then we normalized the data by the population in each state to get the real death rate, which now indicates that DC is the state with the highest death rate, but not the California. Then we want to check the trends and distribution of death numbers through drug types. In this graph, we can see that the number of most kinds of drugs is increasing, except the methadones. Moreover, we can also check the box plot to see the distribution. From this, we can see that among the 7 types of drugs, those related to opioids account for a significantly higher number of deaths, which also match with the trends we get before. Finally, because we have 2 columns of value, one is predicted value, the other named is data value. So we know that predicted value is from the data value, but we try to figure out the difference between them. So we can see that the difference is slightly, but it's growing up, especially after 2022. It may be because that started in February 22, the CDC shortened 6 months prediction lag to 4 months.
For the base learning, we start from doing pre-process by dropping out the OD count because it is an underestimation of the actual death count, and also we will want to enhance other variables' predictive power, and then we convert categorical variables into binary variables. And there's a notation that the 4 states do not have records in the data set, so they are not considered in this case. And at first, we try to feed simple linear regression into the data, but then we found there's overfitting. Then we try to use lasso, but in this way, we found that many features have 0 coefficients, and that's not what we want to see. So we use ridge regression, and we will be able to see each feature's contributions, and that's why we choose this regression. And here's the result. For this result, we can see that the result is not very optimal, the error is very big, and also that there are some negative prediction values appearing in the results, which we will try to solve during the deep learning process.
Next, we'll talk about the architecture that we use. So earlier we have tried linear models, which were not performing that well. So we wanted to try out more advanced and more complex algorithms. So the next thing that we tried was a feed-forward neural network. The architecture was sequential, and we tried out different types of architectures. Permuting between different number of layers, different number of neurons in each layer, and so that was the architecture in general.
To find the best way to train our model, we test 3 optimizers, Adam, RMS prop, and the stochastic gradient descent. Since we are in a regression setting, we are using the mean squared error as our loss function. And to find the best combination of hyperparameters for each optimizer, we use the grid search with a 4-fold cross-validation to avoid overfitting. And our metric to find the best combination and the best model is the mean absolute error.
For the next step was to tune hyperparameters on all the architectures that we found, and we used we tuned majorly 3 important hyperparameters, which were learning rates, the batch size, and the learning rate, momentum, and epsilon. And we also experimented with batch size and the number of epochs, but we decided to go with 10 epochs, and we mostly focus on learning rates, momentum, and epsilon. We saw, based on the result, we saw that the learning, if we increase the learning rate a lot, the model variance increases, which is expected because when we have a very high learning rate, we may be skipping over some important local minimas, while if we had very small learning rate, we were potentially getting stuck in some local minima. And the next parameter that we optimized was epsilon, which is basically a small constant that is added in the denominator so as to avoid divisions by 0, which did not make a lot of impact on our model. The next hyperparameter that we tuned was the batch size. It is expected that a higher batch size will result in a lower variant performance because it is expected that, but using a batch size of 128 gave us the best result.
When we look at the performance of the model on the training dataset, we get a mean absolute error of 52 deaths, which is a fairly good metric considering the large range of values. However, the model seems to be biased and underestimates the number of deaths when the actual number is high, so there is room for improvement finding trends in this range of values. Looking at the performance on the testing set, we get a similar performance and a close MAE of 53 deaths, which means the training was efficient, the model is good at generalizing, and there is no underfitting or overfitting. So we also noticed that the relative error on the test set is not optimal. So we went deeper and found that it was very low for the high values, above 1,000, and rather high for small values. We checked that this level of error was similar on the training set, which means that there is room for improvement to train the model. When we read the individual SHAP effects of the features, we see that the indicators of opioids, synthetic opioids, in the states of California, Illinois, Ohio, and Florida have positive impacts on the predictions, while the other drug types have a negative impact on the predictions. These effects match our observations from the data exploration part. This means that the model was capable of catching the trends from the features. We have learned a few things through this project, including taking the time to understand how the features are built and how the data is collected so we can make sound decisions on how to select the data. And we also mastered the notions of batch size, epochs, k-folds for the cross-validation, as well as the variance and bias of estimation. For the code, the main challenges that we had coding were learning how to mix sklearn in PyTorch and use the Scorch environment, as well as properly saving the optimal parameters and models for the other notebooks.